Okay, good morning once again. Today we will see the S parameters and this is typically qualitative analysis. Means that need of derivations may not be necessary how to arrive these S parameters, but using this S parameter what we can do and what kind of problems we can see it in the microwave network analysis or in general passive devices, micro devices. Okay, so this S parameter, the expansion is scattering matrix parameter. So this what is that scattering is typically this is S parameter used in network analysis in more specific microwave network analysis. Okay, one of the thing is why we need to analyze it any network, that also microwave network. So basically the analysis is if I give some voltage and current to the input or in terms of power into the network, what has to going to happen in the branches or in the output. So I need to analyze it basically, because when I want to design some circuits, I have to know what is the voltage current impedance is flowing on that and what is the gain and all those things I can find out basically if I able to analyze the network. In the low frequency analog circuits, typically we used at many theorems like Norton, Thevenin theorems, and there are parameters. In terms of parameter, I think you would have seen that Z parameters. I'll write down. This is our low frequency network parameters, or I'll put network analysis parameter. Okay. So the low frequency in the sense the operating signal frequency is less. In that case, we have used that Z parameter, okay, and Y parameter, and there are H parameter, and that is ABCD parameter. Okay. So these parameters basically used to relate the voltage and currents in the circuits. So typically if you take the two port, this need not be only two port, it can be extended to many ports. If I take the two port device, so what is means to port? So port is the basically the what are the way the signals can enter and exit from the network, that is the ports. We call as a two-port network if you have an input given as here and output is taken here, or input is given as 2 and output is taken as 1. So if you take this the two terminals, means that two pair of terminals. So if I able to send any voltage here, for example, let us take another color. This is my V1, this is my V output voltage, and this is my current I1, and typically the current flowing out of here is I2. Okay, so if I wants to now relate this with Z parameters, how would I write this? So Z is nothing but basically the voltage by current, that is impedance, basically voltage by current. So what is the impedance parameters here is for two port network, I will write it in the matrix form. If the port are 2, means that if there are two pair of terminal, or if there are two way it can enter or exit in the network, we call as a ports. So here there is one port and so there are a second two ports are there. It's a general network. There are only two ports. It's not only two port, it can have a three port, 4, 5, 6. Minimum we need at least two ports for analysis. Fine. So here, if it is a two-port any network, we will get a 2 cross 2 matrix. That is Z11, Z12, Z21, Z22. So this can be as similar. We can write as like just this is my I1, this is my minus I2, and this is my V1, this is my V2. Okay, so typically then sign you can ignore if you want to calculate the impedance. So the positive or negative impedance for two ports, negative sign you can ignore. So basically this is a simple Z parameter. Similarly you can write Y parameters. So how I've written is here, I've written as like a Ohm's law. This is my I, this is my Z, is nothing but V. So V equals to I into R. Fine. So the input voltage and output voltage V1 and V2 can be related with the current, input current and output current with the Z parameters. So this is a simple phenomena in the network analysis for low frequency. You can find all the values of Z parameters as same like what how you do it in the matrix analysis. So in case if I want Z11, so what I have to do, first I have to expand this matrix in terms of the linear algebraic equation. So one thing you have, we know that from the mathematics, when I write anything in the matrix form, it is a linear. Okay, that is what important underlined here. So this is a linear algebraic equations I can write. So how I can write the equation? I can actually write two equation, algebraic equation, that is typically I will take numeric Roman letter 1 and Roman letter 2. How I can write from the Roman letter 1. So what I can write here is typically Z11 into I1 and multiply with this, no, Z12 into I2 equals to V1, and the second equations can be I1 into no Z, sorry, Z21 into I1 plus this can be Z22 Z21 and Z22 into I2. Okay, this is I1 1 2 I2 V1. This is Z21 into I let me Z21 into I1, Z22 into I2. This is nothing but V2. Fine. Is that clear? So I can do the matrix multiplications. When I do that, I will get a two algebraic equations. Just put me in the chat if it is clear. If it is not uh, correct, if not correct, just put it in the chat. Okay. So here I have written these two Z in a Z matrix with the current. So I'll get related to the voltage. So I hope it is clear. Z21 I1 and Z22 I2. Okay, fine. So I'll get this is 1 and 2 equation. So from this I can find out what is Z1. So from 1, so from 1 I can write Z1 known as, okay, first I'll do one by one. Z1 plus I1 which is equals to let us say this V1 minus Z12 I2. Fine. So Z11 equals to V1 by I1 provided that I2 equal to 0. Is that correct? So what does that mean? If I take the two port network of Z11, Z12, Z21, Z22, and if I provide this V1 and V2, and if I know what is the current I1 and I2, okay, so the Z11 can be written as the voltage difference between V1 divided by I1 as similar like a Ohm's law, and I'm assuming that I2 equal to 0. Okay, so I2 means there is no current. Probably if I change the notation, no, direction, it will be more clear. So if I take I2 in this direction, so time being you just directions you can keep it like probably later. So if you take that I2 equal to 0, it means that there is no current is flowing from outside to the inside. So means that these my two port devices unidirectional. So many cases when we see that in the networks apart from the feedback circuits, If it is that the linear, if it is a non-feedback circuits, there won't be any possibility the current coming from outside to the inside. So most of the practical cases, I can take the current from output to the input. If it is not zero, that means that the current is flowing one direction. Okay, so in that case, I can simply write Z1 equals to Vn by I1. Similarly, I can write Z22 is V2 by I1. So Z12 as V1 by I2 and Z21 is V2 by I1. Okay, so this is actually typically voltage by current ratio. But these Z parameters will help me to relate this voltage and current, input and output current. So what is the use of these parameters basically? So if I have this matrix values, for example, let us take some value 50, 20, 30 and typically 40. So if I know what is the Z11 and Z22, I can actually find out if I know, for example, if I know the voltage, what is how much voltage I'm giving, 5 voltage, and if I know that Z11, I can actually find out how much current is there inside, how much current is going to flow inside the two-port network. And also, for example, if I Z12 is there, if I know what is the Z1 value, Z12 is here is 20, and if I know what is the input voltage, 5 voltage, I can easily find out what is the current will come from the this output of this device basically. Okay, so this is basically the advantage of having knowing the parameters. So if I know one quantity, I can find out other quantity. So typically I know what is the input generally. Okay, so I can find out actually what is the output in the two-port network. So the parameters actually help us to identify what is the node voltage and current in the networks. Typically, it's relating the output and input basically. So this is a parameter. Is one of the what I mean to say, it is one of the blueprint of the two-port device. If I know this is a parameter, I know everything about the device. So input can be anything. I given 5 voltage. Next time I can give 10 voltage. No problem at all. It is like a behavior of the network. It is actually the quality of the network. Basically, if I know that, I can actually predict it basically how it will actually behave. That is the reasons we have parameters in the networks, and also we have it in the microwave. So it's typically when we go to the microwave, we use that. Apart from these parameters, Z and Y and ABCD and H parameters, I think if you know that Z parameter, I think if you recollect, you would have used in the transistor small signal models. Basically, this is will be used to it's going to relate that typically transconductance and basically I by V. No, for example, in a MOSFET, you're sending a voltage and you are getting a current basically. When you write the small signal model, so you apply the gate voltage and you know what is the drain current. You are relating this voltage and current basically. So typically, you can either use the Z parameters or Y parameters. So here, when you realize that. Coming to realize that when you take the H parameters, it actually will help you for a transistor and MOSFET basically, especially in the transistor, you'll use the S parameters to analyze that what you will get it basically, the H values. So from that you can easily do that analysis in the small signal. So basically this is the advantage of having S parameters. So here when we go look into the microwave, we use that S parameter. So that is what the area of interest today. So what is the S parameter? Okay, the S parameter is typically the need, the need has to arise why we need to go for S parameter. We have that number of low frequency parameters. So what is the need? What is the need for S parameter? Okay. So typically, if you take the higher frequency signal, we have seen that extensively in the transmission line, the voltage and current is going to change very fast because the frequency is very high. So if you wants to, if my network, if it is too comparable with the wavelength of this signal, so I cannot exactly know the voltage and current for exact nodes. So here it becomes the job is very difficult. I'm not saying it is not possible, it is difficult. Still, we can write equivalent voltage and current. If you take a coaxial cable, we can still write voltage and current for one point to another point. It is still possible, but it is not easy, basically. Okay, so that is the reasons there is alternative way of representing this network for higher frequency. So one of the handy parameter is S parameters. So S parameters deals with two-port network, beginning with two-port, and it can be extended to multiple port. So I have a two-port network, and here I have similarly like voltage, current, everything will be there. So instead of writing the voltage and current with respect to the ports, I'm going to write my familiar term in the transmission line, the incident wave and reflected wave. Is that clear? So what I'm going to write is here how much wave is incident in the first port, how much is going to reflect. Okay. Similarly, this is the first port. Similarly, how much voltage is incident? Wave, not voltage wave, especially in the second port, and how much is going to reflect. So from this, I'm going to relate this. So you can actually relate this to reflection coefficient. The reflection coefficient also we have deals with reflected wave, voltage wave. This is voltage by incident voltage wave. Okay, so the reflected wave, typically what is the notation? It is reflected negative and incident. This is V plus. That what we have seen as a reflection coefficient. And typically if you want to coefficient is taken a mod value, so we'll get V1 minus mod and a V plus mod. Okay, I just need a magnitude of this, then I will get the reflection coefficient value. Typically it is vary from 0 to 1. That what we used in the Smith chart and in the polar format. We found that the input impedance and other parameters. So basically this is closely related to the reflection coefficient, this parameter. So if I write this S parameter for a first port, okay, and first let us start with the matrix itself. So S parameters can be written as for two port device, the two port. So S11, S12, S21, S22. Okay, so which is equals to okay. S is basically reflected by incident. So this is I can relate as S. So how I can write the matrix form? So V plus I can bring it here. Okay, so it should be a V plus. So V1 plus this is and this is V2 plus, and this is V1 minus and V2 minus. Is that clear? So same S matrix in the reflection form I'm writing in the matrix. So for a two-port device, the reflected wave, I mean to say this reflected wave from any ports, basically I'm writing in general V minus, which is equals to the S parameters or two matrix or and just written in the shorter form. It can be 2 cross 2, 3 cross 3, 4 cross 2 based on the ports, and which is equals to V plus. Can I write in the matrix form? This is same like this reflection coefficient. So any port, the reflected wave which is equals to the value of the incident and based on the S parameter value of the device. So S parameter is a blueprint again for a high frequency microwave devices and networks. So if you take that uh, into the point, so we can similarly we can expand this matrix into the linear algebraic equations. Then I can write two set of equations. From that I can find out what is S11, S22 and S12 and S21. So this becomes a more mathematical. Let's come to the conceptual. Okay, I know that S parameter is there. I know that low frequency parameters, many are there, and this will give a very beautifully relating. It's a blueprint, a behavior of the network or devices. I can exactly know actually if I send any voltage, what will be the output. So that is good, well and good. How it is more practical, you used either in the lab or in the practical high frequency designs. Okay, so one thing we have to keep it in mind, any device cannot act alone. It has to be connected basically, either antennas or we have a transceiver, transmitter, or receiver structures. We need multiple devices to be connected together. So it becomes a network problem now. So in that case, it's more practically relevant. And if I take that matrix into the expanding it, so I'll take this. I'm going to expand this as an equation. Okay, so let us write. I think you are good in the mathematics, so I'll just try to correct me if it is S12 and V2 plus, which is equals to V1 minus S21 V1 plus and S22 V2 plus, which is equals to V2 minus. This is two equation. Let us 1 and 2 only. Okay, so here let us come to this value. What is S11 and S22 and S12 and S21? Okay, so this is my objective is to find this small a, small b, small c, small d. Okay, how to find out from this equation? So let us start with the first one. So how to write S11? Can I just V1 plus and this is V1 minus? I can bring these terms to the right side, become S12 V2 plus, and what is this S11 again? V1 minus by V1 plus. It is coming, no? I think there is no mistakes. You can relate with the comma. Okay, that provided that V2 plus equals to 0. So remember this is very key things. Remember. Okay, I'm keeping this V2 plus is 0. Similarly, I'm going to write what is 1 2. S12 also I can write with the first equation itself, right? S12 V2 plus is equals to V1 minus S11 V1 plus, and what is S12? It turns to be V1 minus by V2 plus, and provided that V1 plus is 0. Again, this is the key thing. Keep it in. Okay. Similarly, just correct me, S21. Similarly, I can write V2 minus by V1 plus, provided that V2 plus is 0. Again, this is key thing. Okay, and the next one S22, which is equals to V2 minus by V2 plus, provided that which is 0, V1 plus is 0. Is that correct? S22 is V2 minus by V2 plus, provided that Vn plus is 0. Okay, these are the key things. Fine. So here, let us come to the more practical experiment things. Okay, so very good, nice. I've remembered those things I've written. I have not actually mugged up these things. So okay, well and good. I've written these equations. So what is that use or importance of this for experiments or for a practical situations? So let us go with the S11. Okay, that I'm going to pick this S11. I'll just keep remember S11 is V1 minus by V1 plus, S12 is V1 minus by V2 plus, S21 is V2 minus by V1 plus, and S22 is V2 minus by V2 plus. Okay, so here what is that S11? So S11 is V1 minus by V1 plus. So this is mean to say, provided that what is that? Provided that V2 plus is 0. So I mean to say, if I take the two-port network and I am supplying some voltage, incident voltage wave at first port V1 plus, and reflected, I will use some other color, reflected from this first port is V1 minus, and I will take that again, that reflected from the, let us take the other color, reflected, I will take the other color. So if the reflected from the second port is V2 minus, and incident to the first port is, sorry, second port is V2 plus. Okay, so if I take the ratio of the V1 minus by V1 plus the first port, okay, this will give me that how much reflection is happening in the input itself. This is a quantity to measure whether this network is perfectly matched or not. Is it able to understand? Like I don't know. I look the network this as a black box. I don't know exactly what it can be a isolator or it can be any device. I'll take any two port device, isolator, it can be isolator or it can be alternator. This is also two port device, the microwave passive devices, or it can be a, let us take the filters also two port network because input and output only two ports is there. Okay, power divider is not two ports because you give an input, the power will be divided into two. That is a three port network. Okay, so this is a power divider is three port. So we have a 3 cross 3 matrix. Okay, so there are other many examples for two port network. We will see it one by one. I don't know exactly. I will look this two port as a black box. I don't know what it is. But if I know that S1 known, I can tell that whether this network is input is matched or not. How it is? If there is no reflection, the V1 minus will become 0. So S11 becomes 0. I mean to say, if I have the S matrix of this any two port device, it can be anything. So if I have that S11, where is S11 will come? Here in the matrix. Because this is S11, this is S12, this is S21, this is S22. Okay, if I know that S11 of two port network, if it is 0, I can 100% say that this input is perfectly matched. Okay, this is a very good blueprint of looking the devices. I even don't know, no need to actually experimentally test it, because when I make this no device, the manufacturer will give me the data sheet of what is the S parameters, or I will tell you in other way they will give it basically. So with that I can 100% make sure that it is perfectly matched. Okay, that input port is perfectly matched. That is more advantage, more useful by having the S parameter values. So that is one thing. And okay, how practically whether they will give S matrix? I will, if you remember the waveguides, now when I show the data sheet, they do not give the S parameters. They've given a different. They've given a VSWR and return loss. The VSWR and return loss is nothing but is related to S11. So whatever you are going to do the lab in the patch antenna, VSWR and what you say that return loss is nothing but what we are seeing is in the S11. It is nothing but what all are closely related. Okay, whatever you have seen in the transmission line, everything is closely related. S11 means what? So S11, and one more thing you keep it in mind, this is only the ratio of voltages. It can be a complex. S11 can be a complex number, but if you take the magnitude of it, it is same as gamma 11, means that reflection. Need not be 1, you just put 1, that is enough. The reflection is first port. Again, this is a mod. Okay. So the S11, if you take a magnitude, is nothing but the reflection coefficient in the first port. It is a measurement of how much reflection is going happening in the input. So these can be taken in a 20 log of gamma. So it can be 1 or it can be 20 log of S11. So this will give me the return loss. Okay, is that clear? S11. So what is that? I'll put the negative sign sometimes to make it return loss is not desirable, because I don't want any no loss is happening through because of the power is coming back. Sometimes they'll put negative. Okay, in the patch and also you have seen the return loss plot like this. You have a frequency here and you have a return loss here, and there are typically you are going to simulate for many frequencies. Let us take from 1 gigahertz to 15 gigahertz. You will simulating the antenna. So if you have designed the antenna in 10 gigahertz, for example 10 gigahertz, my return loss is exactly 0 dB. I write it in the dB. If I design the antenna in 10 gigahertz, I should get a very minimal return loss on that. Okay, so minimal means what? The gamma 1 or S11 should be very less. If it is ideally should be 0, means that there is no reflection. I get a log 0 is infinity, so minus infinity. But practically I may get some value. Let us, if you put some value 0.01 like that, how much you will get return loss? If gamma 1 is 0.01, so this is a mod gamma. So how much you will get? 20 log of 0.01. It's 10 to the power of minus 2. Minus 2 I can bring it into no, up, out of log, so minus 40 dB. So my return loss become minus 40 dB. If I take gamma 1 is not gamma 1 is 0.01 or S11 is 0.0. We can now itself we can easily identify. The practically when they give any devices or antennas, they will mention only the return loss plot. So indirectly they are giving the S parameter value. Indirectly they are telling what is the gamma. Okay, so instead of 0, if I have 0.01, that is what I am writing here basically. Okay, practically it is not possible to get 0. So no device ideally will work in the microwave. There will be always small mismatch will be there. So there will be small reflection voltage will come back to the input itself. It is not huge. Probably if you send 5 voltage, you may get in terms of in practical case, you may get some 1 milliwatt or 0.01 millivolt like that in the reflection. So that is the practical values. So that is better in practical. More than minus 15 dB return loss is good. Basically, it is good, reasonably good. You can go with that basically. Okay, so this is a more practical aspect of seeing S parameter S11. This is closely related with the return loss. How it is closely related with the VSWR? So I know that gamma and VSWR is related. So VSWR will put S, simply S. To avoid the confusion with S parameter, I'll write VSWR itself. So this can be written as 1 plus mod gamma. This is 1 minus mod gamma. So what is the ideal value? Gamma is 0. So 1 plus 0, 1 minus 0, 1. VSWR is 1. Typically I should get 1, but practically I will get more than 1. So worst case is infinity. I think we have seen that VSWR. So the return loss, gamma, S11 are related. You can easily understand these all are conceptually related. So now our focus is S parameters. So we have seen that one of out of 4 we have seen what is the use of the S unknown, and this is related to the return loss for more practical uh, the coefficients what we will say. So if you take for example isolator, they don't give S11 value, they will give return loss. Okay, that doesn't mean that it is S11 is known basically. So similarly S21 is a V2 minus by V1 plus. How to remember this ratio? The first number is always the reflected. And also I just want to point out this Sij. With that I may stop, probably have other class. So here my two ports 1 and 2. Okay, so this I have I and j I given two ports. It can be 1 2 or 2 1. Maybe I just put ij. So always this first number will tell me the reflected voltage wave. The first number I. The second number will tell me the incident, that is incident from input, this reflected wave from the output. So what is that S21 means? What is the reflection is coming from the second port? Means that what is the output at the second port, and the input is the incident at first port. The input is here. So this is more like a general case. I'm giving input at first port and taking output at the second port. Which S parameter will be related to these two is S21. That is V2 minus. The first number will be always the input. The out. What I'm taking. Okay. Output. Okay, S21. The first value will be always the output. The second one is like where it is coming, the input. Okay. So the V2 minus and V1 plus. Is it clear? And S11 is the output is 1, input also is 1. So this is V2 minus and V1 plus. First number is output, the second number is input, V1 plus. And this is more like a giving input and taking output. I'll tell you in the probably in the what is the practical significance of it. So similarly for S12, S22 is what is the output at second port, what is the input to the second port. This means to say I'm giving input here V2 plus, and I'm taking output from the second, that is V2 minus. So V2 minus by V2 plus is S22. Okay, so is that clear? And I have again S12 V1 minus the output at first port, and first number is always the output. from where, that is the second number, that is V2 plus. Okay, the input from the second port. Is that clear? So this is the first number always in the S parameter is the output, and second number is where it is coming, that is the input. So the first number is reflected negative and second number is input. Since it's the input is incident, so it is a plus. Output is coming out, it's a reflected, so it is a negative. Okay, is that clear? The nomenclature is clear. So there are S11, S12, S21, S22 in the S matrix. So this is a short the intro I gave. We have seen only S11. So this is related to the return loss and VSWR and reflection coefficients, which is normally used in the antennas, single port device that I will see that later. There's a single port is also available. That is the antenna. So two port devices, isolator, all no, alternators, filters, or two port device, and power divider is a three port. Four port device is a directional coupler. So that we are all the components you may be using in the lab. Okay, that in the lab experiment you are going to verify these S parameters and with their characteristics. Okay, that what one of the 2-3 experiments related to that. So with that I will stop. I gave only the brief thing. You just analyze that, and we will see it in the next classes. Okay, and take care. And if any questions, you can ask me during the class or later. So with that, I will stop. See you then. Bye.